Okay, so good morning again. Yeah, so I hope you are all getting used to the number of derivations that we are doing so far. I think this entire course we will be doing such derivations and finding similarity solutions. Okay, so it's not so difficult except that you should get used to the notations and things like that. Okay, so tensor notation is one of them which we introduced yesterday. I think if you have time, you please read up a little bit on the tensorial notation. It's not that difficult to understand. Also, you should have some basic knowledge of solution to ordinary differential equations, because in all the similarity solution problems we will convert the partial differential equations into an equivalent ordinary differential equation and find the similarity solution. So that has to be done numerically, and I expect I will be giving some assignments where you have to solve those ODEs numerically by some techniques. Okay, so otherwise if we just stop there and give you the solution, you may not appreciate exactly how the solution has come, and it will all look too mathematical. Okay, unless you do it yourself, you will not appreciate the solution process. So we will look into the second law of for a closed system. So we were till now deriving the conservation equations. We were looking at two different approaches. We started from a Cartesian coordinate control volume and derived. In the other one we had a coordinate free representation, applied Reynolds transport theorem to a closed system and converted the closed system rate of change of properties to rate of change with respect to an open system, and that is another way of deriving in a coordinate free representation. So after we have looked at the first law, it is also very important to look at the second law, because as we all know, most of the times we stop with the first law without too much of botheration to the second law. But if you look at any practical heat exchanger device, entropy generation is very important. You know, there are a lot of irreversibilities within the system, and we have to quantify to some extent the extent of these irreversibilities, and we should also identify what are the sources of the irreversibilities. Okay, so that's where we are going to apply the second law. And we are going to derive a conservation of what is called as conservation of entropy. Okay, just like you have conservation of mass, momentum and energy, so there is also a possibility of deriving conservation of entropy, and that's what we are looking at here. So we start with applying a Clausius inequality for a closed system. Okay, and if you express this in the form of a rate equation, so you know that the total derivative ds by dt should be greater than or equal to 1 by t into the differential amount of heat transferred. Okay, so I will just represent this as delta q dot. Okay, now let us apply the Reynolds transport theorem to express this total derivative for a control mass with respect to the partial derivatives in a control volume. So you can define a property called a specific entropy. Okay, and in the Reynolds transport theorem, the alpha is a property per unit volume, right? So then that can be expressed as rho times the specific entropy. Okay, so we can expand this using the Reynolds transport theorem like this. Now the right hand side applies for an open system. Okay, so now for an open system, therefore if you substitute this Reynolds transport theorem expression into 1, so this is your equation which defines the conservation of entropy for an open system. Okay, so this is nothing but conservation of entropy for open system. Okay, or you can also, if you don't want to look at this as a conservation of entropy, you can also look, think this as an entropy balance. Okay, entropy balance equation. Okay, so now what we are going to do, all the surface integrals can be converted to volume integrals by Gauss divergence theorem, and therefore we can further put this, I can take the integral over v out, so d by dt rho s dv plus this will be again a divergence operation right here. This will be del dot rho s v, okay, and I am going to bring this to the left hand side here. So this will be again minus del q, okay. So this is actually a vector right here, so I am just going to give this vector notation, okay. So this is all integrated over the differential volume because I have already applied the Gauss divergence theorem. So on the right hand side, that should be equal to the rate of generation of entropy, okay. So therefore I can also say that if I express this in okay, or maybe I can also look at this way. I want to look at the entropy generation for the entire volume, so I can also bring this inside minus s dot gen, okay, dv equal to 0, right, so that I can separate out the integrand, okay, and write finally a partial differential equation, okay. So strictly speaking, this entropy generation is per unit volume here, rate of entropy generation per unit volume. So if I can multiply by delta V, okay, so I can say this can be multiplied by dV, okay. So then I can put this on the left hand side, group all the terms together, and that can be equal to 0. Therefore the integrand has to be 0. So then this will give me my s dot gen should be equal to d by dt of rho s dv plus this, which I am going to write in terms of the total derivative notation, which is rho ds by dt, okay, minus del dot delta q, I think this should be delta q by t, okay. I think I omitted by t because that is there in the Clausius inequality, okay. So this should be del, so this divergence operator is on this entire term, okay. So this is how I finally can calculate the entropy, rate of entropy generation. Now provided I can also expand this particular divergence operator on del q by t, so I can rewrite this a little bit. So I can express this as s dot gen is equal to rho ds by dt plus 1 by t del, so I can expand this, I can split it up into, I can take 1 by t out, del dot I can write this as del q, that is 1, the other term is 1 by t square del q dot del t, okay, right. So because this is a gradient operator, so gradient this is a divergence operator on a vector, so this has to be a scalar, so therefore you should make sure that you only get scalar operators out of. So this is again a vector dotted with vector, you basically get a scalar here, okay. So you make sure that the final resulting operation also is consistent with the original operator. Is that clear? The splitting up is clear, okay. So I am just so if you have a gradient the same way that you write, you have to write the same way for a divergence operator also. Only thing you should make sure the resulting operator is also scalar, giving you a scalar, okay. So therefore now what I can do here, so now I am going to evoke the Gibbs theorems, one of the Gibbs theorems, if you can remember. So for a closed system again, you know that du is equal to Tds minus Pdv, okay. So I am going to write as Pd into 1 by rho, okay. So this is coming straight from your first law, right, where you substitute Tds for delta q and you have Pdv work, okay. So this I can write in terms of the rate equation, and you can tell me how this should look if I want to write ds by dt. Okay, so if I express ds by dt, so I can write this as du by dt, so I can take 1 by t on the other side minus, so this should be, if you can express this as d rho by dt, so what should be the remaining term? Rho square and t, right? So I am taking this t, dividing it all the side, so I am now going to multiply this by rho, okay, throughout, so that this we can be written as so this, there should be a p here, p by rho t, right? So this is a little bit of manipulation to suit my convenience here, because now I have to find some relation for rho ds by dt. So I am just expressing this from the Gibbs equation, okay, I am connecting that to the change in the internal energy and the change in density with respect to time. Now if you look at incompressible flows, okay, for that this has to be 0, right? So there is no change in density with respect to time, therefore the change in the entropy has to be directly the change in the internal energy of the system, that is directly linked there. So let us also express the first law now. If you write the first law, so you write d rho du by dt should be equal to minus del dot q, okay, plus mu phi, okay. So I am writing in the final coordinate free representation, okay. So instead of saying del dot q, you can also say del dot del q. In fact, if you want to maybe rewrite to just avoid some confusion, you can also write this in terms of yeah, okay, just to avoid some confusion you can express this as q instead of del q here, so that finally it is consistent with that. Maybe you can do this small change, okay. Okay, so both are consistent, all right. So therefore what I am going to do now is to substitute for rho du by dt from this expression into this, and this I am going to substitute into this, okay. So the resulting expression will be s dot gen will be, so this will be basically rho ds by dt is nothing but rho by t du by dt, which will be minus del dot q by t plus mu phi by t, okay. So that is this term plus you have these two terms, right, plus del dot q by t minus 1 by t square q dot del t, okay. So these two terms cancel off, so therefore your final expression for s dot gen turns out to be, if you can also now substitute the Fourier's law for q as k delta t and express this as minus, okay. So this is minus of q dot which is again minus k delta t, so that will become k delta t square divided by t square, okay, plus mu by t phi, okay. So therefore the components of entropy generation are two. So one is coming from the entropy generation due to the conduction part, okay. So within the system the conduction of heat, the other is due to the viscous dissipation, okay. So this part till here I think it's straightforward, only after this we apply the Gibbs law and just manipulate a little bit so that we can eliminate some of these total derivative terms, okay. So finally we write everything in terms of the heat transfer by conduction and the viscous dissipation. So now there was this person called Adrian Bejan. I think there is one textbook also which you are referring, convective heat transfer. Okay, so he came up with a very ingenious method that he wanted to give a non-dimensional number which is actually referred to as the Bejan number. Okay, so this is called Bejan number. So notation is given as BE. He wanted to look at the contribution of the entropy generation by means of conduction, okay, as a fraction of the total entropy which is generated. Okay, so that he has taken this term on the numerator divided by this entire thing on the denominator. Okay, so this is called as Bejan number. In fact, the idea of entropy generation due to heat transfer was his idea. So this derivation actually is done by him, and there is also a paper in 1990s, with a student where he has derived this expression for heat transfer, irreversibility due to heat transfer. Okay, and I think the Bejan number was credited to, it was basically given due to his contribution for this work particularly, and this measures if your Bejan number is some value, say about 2, it tells you that the majority of entropy generation is through by conduction. Okay, and if it is much lesser than 2, it tells the majority of entropy generation is through viscous dissipation. Okay, so basically this can be plotted just like you plot your isotherms and heat flux lines. You can plot the entropy generation due to each of these, and you can visualize and see how it looks. Okay, it's a very useful tool. And you can see where the in which location in a particular system your entropy generation is by the conduction part and where it is by viscous dissipation, and if you can probably try to reduce the viscous dissipation by some method, so that will also reduce the entropy generation. Yeah, both are dominant kind of thing. Both are equally important. Okay, so any questions? I think I wanted to just finish the governing equations, therefore I wanted to touch upon the second law also, apart from the first law which you are already familiar. Okay, so I think many of the textbooks don't talk about the second law conservation and things like entropy generation much. Okay, so any other questions on this, any doubts, anything that requires some clarity, or is that okay? Okay, fine. So then we will proceed to a new topic now. Still we are in the introductory portion of this course where we are deriving the conservation equations and so on. So you have seen that the Navier-Stokes equations are quite complicated, so we cannot solve them analytically except when we are making some approximations. Now we can also bypass this, and we can introduce another set of equations which can be solved in place of Navier-Stokes equations, especially for 2-dimensional flows and 2-dimensional incompressible flows. Okay, so for 2D incompressible, we have to solve, if you solve the Navier-Stokes, we need equations for u, v and p. Okay, so u, v, p, and if you are solving energy, again temperature. Okay, now we don't have a separate equation for pressure. Okay, we have equation for u and v and continuity equation which is like a default equation. So therefore numerically there are some techniques to overcome this hurdle where we construct an artificial pressure equation and things like that. If you want to overcome that, we can rewrite the Navier-Stokes equation into what is called as a stream function vorticity formulation. Okay, and that is very useful when you are looking at 2D incompressible flows. Okay, there you have only 2 variables, 2 equations. You can solve that straight away, and the equation solution is also slightly simpler than solving the Navier-Stokes. Okay, so we will just quickly derive those formulation today, and in fact in the project that you are supposed to do, you will be using those 2D stream function vorticity equations with the energy. You will be solving them numerically. Okay, I will send you some reference papers, and you will apply that to a problem of natural convection. Okay, so now as and when natural convection will be covered, you can, because this is a nice rectangular cavity, so the taking finite differences will be much easier. All right. Okay, so we'll do that now. So the next topic will be for 2D. So this 2D is the approximation that is required. Okay, we cannot write this in 3D again. Okay, 2D incompressible flows. Okay, so let us write down the Navier-Stokes equations first, and from there we will try to derive the stream function vorticity equations. So from the continuity equation, so you have to tell me for 2D incompressible flows, what is the continuity equation? Let us assume Cartesian coordinate system. Okay, so du dx plus dv dy equal to 0. So now the complicated equations slowly will get simplified, as and when we go through the solutions. Okay, and the x momentum du by dt plus would be equal to minus, what about density? Density has to be divided, right? Plus dynamic or kinematic? Kinematic. This is your Laplacian operator, right? So and similarly your y momentum, which will be dv So we will also write your energy equation. After we derive the stream function vorticity formulation, we will quickly go back to the energy equation and simplify that. Okay, so what is your 2D incompressible energy equation? We can directly write for temperature. Okay, plus is equal to alpha, because that is k by rho Cp, which is nothing but the thermal diffusivity. Okay, the thermal diffusivity alpha plus, okay, so now I am going to neglect the viscous dissipation now. Okay, I don't want to put too many terms into this, so I can safely neglect the viscous dissipation. Okay, so this is neglecting okay, so now this is more familiar to you. You have been working with these equations in your earlier courses. Now what we have to do, we have to think a little bit. See, there is a pressure term in the momentum equations, and we want to somehow eliminate it, because as you know that we don't have a separate equation for pressure, and when we want to numerically solve that, we want to simplify this problem. So how can we probably do that? Take derivative with respect to y here, respect to x, subtract these two, right? So that will eliminate this pressure derivative term. So exactly that is what we are going to do. Okay, so we will differentiate x momentum with respect to y. Okay, and so I am going to say differentiate y momentum with respect to x minus differentiate x momentum with respect to y. Okay, so if you do that, so you can group these two terms, the temporal term, you can say d by dt of so you can write this as dv by dx minus du by dy, is that right? Okay, so I am taking d by dt common, so I am differentiating with respect to x minus differentiating this with respect to y, alright. So the other terms, you get lot of terms here, because now if I say I am going to differentiate this with respect to y, so I have to split it up again, right. So this will be minus, you have to tell me now, so this is d by dy of u du by dx. Okay, so I can write this as u into d square u by dy dx minus, yeah, du by dy into du by dx. Okay, similarly this term can also be expanded, that will give you minus v into d square u by dy square, right, minus du by dx into dv by dy. This should be dv by dy into du by dy, I am sorry. Okay, let me check all the terms again. Yeah, okay, so the same thing now I am going to do differentiate the y momentum with respect to x. Okay, so this minus this, right, so these terms will be positive here, so plus you have du by dy into dv by dx, plus you have u into d square v by dx square, plus I am going to differentiate with respect to x into dv by dy plus v into d square v by dx dy. Okay, so when I differentiate this with respect to x, this and subtract, they are going to cancel. Okay, on the right hand side I will have nu into minus d cube u by dy dx square minus d cube u by dy cube plus, so I will have these two terms right here, d cube v by dx cube plus d cube v by dx dy square. Yes? 1, 2, 3, 4, 5, 6. This one dou u by dou x. Yes, you are right, because we are differentiating with respect to x. So all the other terms are correct. Please do this and check once. So I am now going to group these terms together in some particular fashion, and we will see that that grouping will help in reducing. We can actually define a new function which can be substituted for those grouped terms. So I am just going to group like this. So you take common and what are all the terms common to you. So you have this term, you have this term, so I can write this d square v by dx square minus d square u by dy dx. So these are the terms common to you. Okay, so again plus v, now you have to tell me which terms I can group. Dou square v by dou x dou y minus, alright. So we have somehow 1, 2, 3, 4. Okay, so 4 terms we have taken care, and before that, okay, I am going to add the temporal derivative term. So that is d by dt of dv by dx minus du by dy plus these terms, right. So this term is also taken care. Now we have 1, 2, 3, 4 terms which are still on the left hand side that have to be grouped together. So what I am going to do is I am going to take dv by dx common. Okay, so if I take dv by dx, so that means this common, so du by dx plus dv by dy, which is nothing but two dimensional continuity, which is automatically satisfied. Okay, this is a nice trick to eliminate all the unnecessary terms. Okay, plus next I am going to take du, so this is actually minus du by dy out, so du by dy, so you have du by dx and dv by dy, so that will also be satisfying continuity. So this goes, this also goes. On the right hand side I can just group them as d cube v by dx cube minus d cube u by dx square dy. Okay, so I am grouping these two terms, okay, plus d cube v by dy square dx, okay, minus d cube u by dy cube. Alright, so I am just grouping them. Now what I am going to do is to introduce a function called the vorticity, which you are all familiar, right. So how do we define vorticity? Many of you can recollect from your incompressible flows. In fact, you can get a clue from the terms that we have grouped. dv by dx minus, yeah, exactly. Okay, now you can see why we have grouped those terms, because they are going to be directly in terms of the vorticity that we have defined. And now we are going to take derivatives and check, it will come exactly to those terms. Okay, so for example, if you now take the derivative of vorticity with respect to x, now you please tell me what the term should be. That should be exactly the first term on the spatial derivative term, right. So that is del square v by del x square minus del square u by del y del x. Okay, so d omega dy should be what, d square v by dx dy minus d square u by dy square. Okay, that is this term right here. Okay, so now if you take second derivative, d square omega by dx square, can you tell me what the second derivative will be? Okay, so this is this term right here. Okay, so regarding this, rho cube v by okay, and this is dou cube u by dou y cube. Okay, that is this term right here. Okay, so therefore you find that grouping all these terms makes sense. You can write them in terms of the vorticity and its derivatives. Therefore I am going to substitute in terms of vorticity, so this will be d omega by dt plus u d omega by dx plus v d omega by dy should be equal to nu into so this is my governing equation for vorticity, okay, or you can also say that this is the vorticity conservation equation. So have you derived this before earlier in compressible flows? Vorticity, okay. So this is an important equation, and it simplifies because now your pressure terms are not appearing anymore. Okay, now still we are not done, because we have simplified the momentum equations, okay, but the thing is still you have your u and v velocities appearing here, okay, and we have to somehow eliminate them. Stream function. So how are we going to do? We have to define a function which automatically satisfies the continuity equation, and therefore you don't have to again solve for continuity separately, right? So therefore what is that function which does it? That's the stream function, okay. So from the stream function you can calculate your velocities. For example, u is related to your stream function as d psi by dy, and v is minus d psi by dx. So naturally you can see that du by dx plus dv by dy will be 0. So the stream function is automatically satisfying continuity. So you can plug in for u and v in terms of the stream function, and the other thing, the stream function should also satisfy this equation, because this is how the vorticity is defined, and vorticity is related to the velocity terms, the velocity derivatives. So therefore the stream function should make sure that it satisfies this particular definition of vorticity. So if you substitute for stream function into that, so what do you get? So your omega will be, so if I take dv by dx, this is minus d square psi by dx square, and du by dy minus, so minus of d square psi by, right. So you can now substitute this in terms of the stream function, therefore you have eliminated the velocities, okay. So this is your equation number 1. So this is the conservation of vorticity. Equation number 2 is, now since you have introduced stream function, you have to solve for stream function, okay, and that is done by means of second equation which relates your stream function to vorticity, okay. So this is your second equation. So now you have two equations, two unknowns, right, one for psi and the other for omega. So this is much better to solve rather than the Navier-Stokes, correct, okay. So where you have to solve for three equations and you don't have an equation for pressure. So that's why it's very popular technique for numerical solution to two-dimensional incompressible flows, okay. Most of the journal papers that you take for 2D incompressible flows still until recently, okay, where you didn't have powerful computing facility to solve the full Navier-Stokes equations, they were employing the stream function vorticity technique, okay. So and this is what you are going to try out also. Now the same thing in energy equation if you substitute, okay. So apart from the flow field, you can also calculate for temperature. So the energy equation becomes, you can substitute for u again in terms of stream function, so this is your energy conservation, okay. So you solve for three equations for three unknowns, omega, psi and temperature, okay. So these are the equations that you exactly have to solve in your particular project, and I will be giving the papers. You have to apply the corresponding boundary conditions to solve this problem. So for a particular problem you have to do it, and then you can probably look at steady state solution where you don't have to consider the time derivative, okay, only the spatial derivative, and you can do this iteratively. So there are a couple of techniques like Gauss-Seidel or Gauss-Jacobi iterative techniques which you can do it, and you can use finite difference methods, simple finite differences to basically discretize these derivative terms, alright. Okay, so with that I think most of the conservation equations we have seen, and also different variants of the conservation equations. What I am going to do now is to slowly get into the theme of this course, which we are going to apply for both external and the internal flows. Okay, now we have to make some approximations to the Navier-Stokes equations. When we apply that to external flows, we cannot solve the Navier-Stokes as it is. Okay, so these approximations are called the boundary layer approximations as far as the external flows are concerned. And before doing that, first we will try to non-dimensionalize the Navier-Stokes equation. We will try to define some non-dimensional numbers. We will see what non-dimensional numbers are governing the flow and heat transfer parameters, and we will also identify the regimes based on these non-dimensional numbers. And finally, when we go to boundary layers, we have to use these non-dimensional numbers to make certain approximations. Okay, so once the boundary layer equations are derived, from there we will start our process of solving for different configurations. Okay, so we will I'll just introduce you a little bit. We have some more time, about 7-8 minutes, so I'm going to talk about the different parameters, different variables, and how we are going to non-dimensionalize them. Okay, so I think this is probably familiar to you because you have done this earlier in your incompressible flows and also advanced heat and mass. So very quickly we'll go over it, and you can yourself try to non-dimensionalize. I'm going to write down only the final non-dimensional equations. Okay, so hereafter we will be dealing only with incompressible flows, and that also in 2 dimensions. Okay, so all the complicated terms will be dropped off, and only will retain terms in these 2 dimensions. So 2D incompressible. In fact, I shouldn't have erased the Navier-Stokes, so the same thing applies here. And anyway, I'll just do it, write it quickly again. I'm going to also include the pressure term. Okay. So here what I am doing is 2D, also incompressible and steady. So this is the approximation that I am going to bring here, because after we non-dimensionalize and apply this to boundary layer flows, we are pretty much going to do this for steady state solutions. Okay, so we will stick on to this particular form throughout. So most of your solutions will be for 2D incompressible and steady state. And also we are including the viscous dissipation here to non-dimensionalize and see what kind of non-dimensional numbers come out. Okay, suppose you take any flow, say past an airfoil or past your flat plate. Okay, so you have your free stream, which is described by your free stream velocity and temperature, and you can also maintain the surface of the airfoil, okay, at an isothermal condition such that your T wall is constant, and let us say the characteristic dimension of this particular airfoil is given by the chord length, which is L. Alright, so these are some of the variables that you have fixed. You have your U infinity, T infinity defined. Okay, the geometry is well defined, and also you are fixing the boundary temperature to an isothermal condition. So with these parameters, how are we going to non-dimensionalize? So as far as the coordinate system is concerned, okay, let us take a coordinate system x and y, okay, like this, which are along the chord length and normal to the chord. So I am going to define a non-dimensional coordinate system capital X which is x by L. Similarly, capital Y will be y by L, and as far as the velocities are concerned, I am going to introduce capital U, okay, which is what, u by u infinity. Similarly, capital V is equal to v by u infinity. Okay. Now coming to pressure, okay, so velocities coordinates are done. So I am just going to introduce a capital P, which is equal to the small p dimensional P divided by. So how do we non-dimensionalize the pressure? Okay, so I am going to cut the half term because it does not make much difference. Rho infinity u infinity square. Okay, so the free stream density is rho infinity. All right, and finally coming to the temperature, I will define a non-dimensional temperature theta such that at the wall the value of the non-dimensional temperature equal to 1, and in the free stream away, so the value should be 0. So how do I non-dimensionalize that? T minus T infinity by T wall minus T infinity. Okay, so that at the location where at boundary T equal to T wall this becomes 1, and at the free stream somewhere that theta goes to 0. Alright. So with this I just write the final equation. You can in fact derive this and check for yourself. If you substitute these non-dimensional variables into the dimensional Navier-Stokes equations, so you are now going to tell me. So we will write down only the final version. So what will happen to the continuity? This is right. I am just substituting for the dimensional in terms of the non-dimensional variables there. Alright, they cancel out everywhere. Okay. As far as the momentum equation is concerned, u du by dx plus v du by dy, I am writing all in non-dimensional terms, is equal to minus d capital P by dx plus something which you have to tell me what it is, d square u by dx square plus d square v by dy square. Okay, the same thing for the, so this is capital U dv dx plus v dv dy minus, so these are all in non-dimensional variables, so you have to check and tell me what terms should be there. And similarly finally you have d theta dx plus I am going to introduce a non-dimensional viscous dissipation phi star. So you have to fill in the blank, what are the terms that are going to appear here. Okay, so what should be the term right here? Reynolds number. So if your Reynolds number is very large, so what happens? This term is more important than the convective term, is that correct? It should be 1 by Reynolds number, right? 1 by Re based on the length. So where your REL is nothing but rho u infinity L by nu, correct? Similarly the same thing comes here, 1 by REL. Now what should be the term here? Just half minute, we are done. Okay, so I am just going to give it, you please check it, 1 by Re Prandtl number, okay, where your Prandtl number is equal to mu Cp by k, which is also nu by alpha. Okay, and finally here I am just going to introduce a non-dimensional number which probably you have not encountered, So this is going to be what is called as Eckert number by Reynolds number here, where your Eckert number is defined as u infinity square by Cp into T wall minus T infinity. Okay. So what I give you as a homework is to please substitute all that carefully and check whether we arrive at this non-dimensional formulation. Okay, I think you can do that directly. You can see that this comes directly straight away. Only this combination and this combination you have to check again. Alright, so we will stop and we will meet on Tuesday. Okay, we'll start with the boundary layer approximation.